Welcome to episode 6 of Adafruit and Digi-Key's All the Internet of Things series, a 6-part program which covers everything you need to know about IoT. Wow, have we really made it to the final video? I feel like we've gone through so much together on this journey, and like journeymen, we are finally ready to apply all the knowledge we've picked up over the series to make a complete project. Over the video series, we have built up our knowledge, starting from the very lowest levels. We started out with transports, where we analyzed the different ways to move bits of data around. We talked about small hop transports like Bluetooth Classics and low energy, Zigbee and Z-Wave, and their use in small-scale area networks such as within a home. We also covered longer-range transports like Wi-Fi, Sigfox, and LoRa that can cover an entire building or campus. Finally, long-range protocols like cellular or satellite that can connect you anywhere in the world. Each transport has different power needs and bandwidth capabilities. Some are handy in that they connect directly to the internet. Some need gateways to access the internet, which can add cost and complexity. Transports directly affect your bill of materials and chipset selections, and it's very hard to adapt a product to use a new or different transports, and transports don't have a lot of overlap in their capabilities, so that's why it's the first thing to pick. Next, we dove into protocols, which is how we program the transport we've already decided on. That episode was a super deep exploration of different transport protocols like HTTP, MQTT, CoAP, as well as encoding methods such as XML, JSON, and base64 raw data. Which one you use depends on your transport speed, bandwidth capabilities, and the data responsiveness you need. HTTP gives you a direct connection to internet services, but with a heavy price in data usage. MQTT is like Nimble with little overhead data-wise, but requires a gateway to get you the data you need to the larger internet. Usually, there is a little more flexibility in what protocols and encoding methods you get to use, and a good decision here can save you money and support later. Once we sorted out our hardware transport and our firmware protocol, we moved up the stack to the software services. Just like protocols encode the data that moves over the lowest level protocols, services package up and direct that encoded data. Services can also store data for later analysis or provide meta services like notifying you by text message when no data has been reported for 24 hours. You could roll your own service, but it's a huge effort, and there's easily 100 different services available for any sort of IoT usage. We covered some of the most popular ones, from Plotly to Carriots, Particle to AWS. Some services are prototyper-friendly or designed with scientists in mind. Others are designed for enterprise-level deployments. We went through examples of using each service so you could find the right match for the complexity of your product. After touring all the different services available, we took a deep dive into our own IoT service, Adafruit I/O. While we focused on just one service, there's a lot of similarities between Adafruit I/O and other services. So even if you end up with a different IoT provider, it's beneficial to see how the pieces fit together. This was also the first video where we provided code and schematics to build a complete project for temperature data logging. We used Wi-Fi as our transport since it's the most popular transport for internet connectivity. The projects were shown with both Arduino C++ microcontroller programming on a Feather ESP8266 and in Python on a Raspberry Pi single-board computer. The Arduino code utilized MQTT as a protocol, and the Raspberry Pi used REST, showing that you can get similar results with both low-power, low-level microcontrollers and higher-power, high-level microcomputers. Together, we went through each step of signing up for an account, making a feed, creating a dashboard, and plotting output data. Then we explored extensions like webhooks, triggers, and Adafruit I/O integrations. After building our first project and connecting it to Adafruit I/O, it was time to cover security, a wide-ranging but important topic that has thankfully gotten more attention in recent years. Security practices are never-ending in complexity, and even as we speak, new IoT security alerts and warnings are being published. So instead of looking at specific exploits or attacks, we categorized different ways that you can protect and harden your attack surface. Some of these techniques are super simple, like having unique, unguessable passwords. Some are more advanced, like requiring bidirectional TLS certificate checks and hardened crypto storage. Either way, following the checklist we provided in the video will do a lot to protect your product, your data, and your customers from prying eyes. Finally, we've reached this video, where we will explore using Digi-Key IoT Studio, an all-in-one solution for creating a complete IoT prototype or project. Unlike most other IoT platforms, IoT Studio is codeless. All the sensor interaction and storage is done automatically by the drag-and-drop IDE. You do not need to install toolchains, code editors, or compile any code on your computer. Digi-Key IoT Studio runs in your web browser and handles all aspects of developing an Internet of Things project. It even compiles that code remotely for you. As we have covered in the video series so far, IoT projects involve programming firmware into a device, sending that data from the device to the cloud, and then interacting with the data and device using a website or application. Digi-Key IoT Studio comprises of 3 workspaces which simplify this development: an embedded workspace to develop and build your device logic, an application workspace to build an application for your device, and a cloud workspace to construct a method to send data to the cloud. This high-level integration is possible because IoT Studio has built-in support for a range of transport boards and sensors. Note that not all boards and devices are supported, but lucky for us, there's plenty of Adafruit products supported already, including our series favorite, the ESP32 Feather and the Analog Devices Featherwing. However, in this video, instead of just a simple temperature sensor data logger, we'll make a complete home automation system that you can follow along by picking up our IoT Studio kit. Now, since I live here in New York City, I don't have a lovely suburban home to automate. And even if I did, it would be really hard to ship it to you in a kit. So instead, we'll be automating this adorable papier-mâché house. The small size of this build lets us explore wiring, user interaction, and firmware deployment without having to get a ladder out. We'll use the ESP32 as the microcontroller brains. It can use both secure Wi-Fi and Bluetooth LE as a transport, so you can make both internet-connected and mobile-connected applications. For inputs, we'll use the Analog Devices Featherwing to get precision temperature readings, and the Bosch BME 680 to get humidity, barometric pressure, and air quality input. We'll also add a magnetic door sensor to detect when somebody opens the door or window. For outputs, we'll use a relay wing to control a fan. That's our way of simulating an HVAC unit that turns on when it gets too hot or cold. We'll also connect some LED lights to a GPIO pin so we can turn on or off the lights at sunrise and sunset or when someone opens the door. We'll program up these behaviors in IoT Studio and then deploy them as a web or mobile-controlled app. The mobile app especially is a powerful capability that is not available for most services. To kick off the step-by-step build, I'm going to put you in the capable hands of my colleague Brent, who is an IoT Studio guru. You can follow along with your own hardware or pick up our kit to build this at home. Then, once you've completed the same project we have, check out the hundreds of supported sensors and devices to extend and expand your IoT project.
Thanks, Lady Ada. This project will require you to have a hardware IoT system to control. We recommend picking up the Smart Home Kit for Digi-Key IoT Studio on the Adafruit or Digi-Key website. Follow along with our guide on the Adafruit Learning System to assemble and wire your own IoT home. You can also DIY your own setup on a breadboard, but it won't look as cute. Before we start using Digi-Key IoT Studio, we need to install 2 applications: the Digi-Key IoT Studio mobile application for iOS or Android, and the IoT Agent application for your desktop computer. The Digi-Key IoT Studio app integrates with the Digi-Key IoT platform. It lets you monitor your connected projects from your phone or your tablet. You can download it for free from the Apple App Store or the Google Play Store. We'll be using it to interact with our IoT home over Bluetooth Low Energy. You will also need the Atmosphere IoT Agent to program your Huzzah32 from the Digi-Key IoT Studio website. Atmosphere is the company which developed the Digi-Key IoT Studio software. The IoT Agent is an application that runs on your computer and sits in a system tray. It's used to communicate between the Digi-Key IoT Studio website and your hardware. Once you have installed both the Digi-Key IoT mobile app and IoT Agent, launch the Atmosphere IoT agent. You should see it in your system's tray or menu bar. Then navigate to the Digi-Key IoT Studio website. Click Get Started Now. You may be prompted to log in with your Digi-Key account. This is the Studio project screen. From the Studio project screen, select a new project by clicking the plus button. At this time, only the Huzzah32 Feather is supported. When you go through this yourself, you may find many more boards. Make sure you click the Huzzah32. Name the project IoT Home and click Create. Once the project is created successfully, you'll be brought to the embedded workspace for your project. Our workspace is blank and ready for us to start creating our own IoT home. First up, we're going to create a mobile application to turn on the IoT home's lights wirelessly from your phone. We'll start by building the embedded firmware, which runs on the Huzzah Feather. We're going to build firmware by dragging and dropping elements to the embedded workspace. First, we'll need a way of controlling the lights from our device. Let's start by creating a new BLE characteristic. This characteristic will allow us to write and read the value of a light switch. From the element toolbox, underneath Bluetooth Low Energy, click BLE GAT characteristic. We should see a new element on the workspace named BLE characteristic custom. We will also want to create an element to control the LEDs connected to the Feather Huzzah. To do this, create a new GPIO pin element. This element can read or write the state of a GPIO pin. From the element toolbox, under Embedded Basic, click the GPIO pin element. Let's select the GPIO pin we'd like to use. Click the GPIO pin element on the workspace to bring up its properties. We will be using multiple GPIO pins in this project, so change the name to GPIO pin 14. Then set the GPIO pin to IO14. Before wiring up these two elements, we'll need to create the application's interface and logic to connect the Bluetooth characteristic and the GPIO element we just made. Let's switch to the application workspace. The application workspace is different from the embedded workspace. It contains an application builder for designing the project's interface and an application workspace for wiring the application's interface and logic. Let's start by selecting the correct display size for a device. From the application builder, click the icon that looks like a phone. Digi-Key IoT Studio supports many types of displays, ranging from phones to Chromebooks. We'll be using an iPhone X in this video. Using the search bar, search for the iPhone X. Click the toggle button to enable the phone's display size, and then click Save. We'll notice that the canvas on the application builder has increased. The application workspace is not empty like the embedded workspace initially was. There's a BLE characteristic custom element on the application workspace. This is the same element created on the embedded workspace. The BLE characteristic element is a coupled element which bridges data between the embedded and application workspaces. When we create a new BLE characteristic element in the embedded workspace, a mirror of this element will be created in the application workspace. We'll want a way to turn our home's lights on or off from the application. To do this, we'll add a toggle switch element to the application interface. From the element toolbox, under Application Interface, click on the toggle switch. Not only will this create a toggle switch element in the workspace, it will also create a toggle switch element in the application builder. Elements on the workspace can be changed together using another element called a connector. Let's use a connector to connect the toggle switch and the BLE element together. From the workspace, reorganize the two elements. Click the toggle switch element. In the Elements Properties window, click the Add Event button. Then select the BLE characteristic element to add a connector between the two elements. Click the gear icon on the connector to bring up the connector's properties. We'll want to send the value of the toggle element to the BLE characteristic. To do this, we'll change the ability of the connector to write and set the value to a special variable which contains the true or false value of the toggle switch. Our application looks a bit boring. Let's give it a beautiful background. From the Element toolbox, under Application Interface, click the Image element. This will create a new image element on the workspace and the application builder. Now we'll need a background. Head over to the Turning on the Lights page of this project's Learn Guide and click the Download IoT Home Background.png button. Save this icon to your desktop. On the Application workspace, click the Image element to bring up its properties. Name this image element Background. Then click the Browse button. With your file browser, select the background that you just downloaded. We created this background for compatibility with the iPhone X or iPhone 11, so we'll select No Scaling to use the image's native resolution. However, if you're using a different device, you may scale the image using the width and height controls on the application builder. The toggle switch should be located underneath the light bulb icon on the background. On the application builder, click the toggle switch and drag it underneath the light bulb icon. Congratulations, you created your first Digi-Key IoT Studio application. Now let's navigate back to the embedded workspace so we can finish our code and upload it to our Feather Huzzah. Make sure you save the application at this point by clicking the Save button at the top right corner of the page. Click the Embedded tab to navigate back to the embedded workspace. Now that we know what the BLE characteristic will be used for in this project, let's rename it. From the workspace, click the BLE characteristic element to bring up its properties. Change the name of the BLE characteristic element to BLE characteristic lights. Since our application uses a toggle switch, we can only send two types of values, an on or an off. These two values are represented by Digi-Key IoT Studio as a Boolean data type, a 1 or a 0. In the BLE characteristics properties, change the read data type to a Boolean value. Then, change the write data type to a Boolean value. Finally, let's add a new connector element between the BLE characteristic and the GPIO element. Under the BLE characteristics properties, click Add Event. Then, just like before, click the GPIO element. Click the gear icon on the connector. On the connector's properties, change the connector's ability to set state. This will set the value of the GPIO pin connected to the LED high or low, depending on the toggle switch's value. We're done with the project, and we're ready to upload the code to the Feather Huzzah. On the top right of the project window, click the Compile button. While typical embedded projects involve running compilation tools on your computer, Digi-Key IoT Studio compiles projects in the cloud. Because of this, the compilation time may take a minute or two depending on the complexity of your project. Once the project is successfully compiled, a green bar at the bottom of the screen will appear notifying you that the project is ready to upload. Next, let's upload code to the Huzzah 32. Make sure the Huzzah 32 is connected to your computer's USB port and that the Atmosphere client is running. Click the Program Firmware button. Select the serial port. The port name will vary between operating systems. Check the guide for more information. The serial port I'm using is called dev/tty.slab USB to UART. Click Program. This window will update when the firmware has been successfully uploaded to the Feather Huzzah. With our program successfully uploaded, let's move on to using the Digi-Key mobile application to interact with our IoT home's lights. Open the Digi-Key IoT application on your device. Tap the Login button and log into your Digi-Key account. The The Digi-Key IoT Studio mobile app is a pared-down version of the web-based Digi-Key IoT Studio IDE. We cannot edit or modify code, but we can connect to our devices and view their status. Tap the cube icon on the application sidebar. This is the devices screen. We can have up to 5 devices simultaneously connected to our Digi-Key IoT Studio account. Let's add the IoT home we just programmed. To do this, tap the Add Device button. We should see the IoT home in the devices in range list, along with its BLE MAC address. Tap the device to connect to it. We're only using this product with Bluetooth Low Energy. On the Configure Wi-Fi settings, tap the Cancel button. We should be brought to the application view. Now that we can turn on the lights inside the home, you may be asking, what else could I do? Using environmental sensors inside a home is a way of monitoring factors which may impact our comfort or our health. We can monitor if the temperature in a room is too low or if gas concentration is too high. We're going to use the ADI Featherwing to obtain precise temperature readings from inside the house. We'll also use a Bosch BME 680 sensor to obtain readings for the home's relative humidity and gas. Finally, we'll enhance the application by adding dynamic labels to display readings from the various sensors inside the home. Navigate to the embedded workspace. We'll start by adding a new element to the workspace, an interval element. The interval element contains a timer which we can set. When the timer expires, the interval element triggers all elements connected to it. From the element toolbox under Embedded Basic, click the interval element. On the workspace, click and drag the interval element underneath the BLE characteristic element to give it room. Elements for the BME 680 or the ADI Featherwing are not in the default element toolbox. We'll need to add these manually from the Digi-Key element library. At the bottom of the element toolbox, click Add Element to open the element library. There are lots of elements available in the element library, all for purchase from Digi-Key's website. Let's find the temperature sensor we'll be using for this project. Search for the ADT7410. We'll be using the ADT7410 Featherwing, not the ADT7410 Breakout. Click the toggle switch to enable the element. Click Save. We should see a new element in the toolbox named ADT7410 Temperature. Click the element to add it to the workspace, and move it to the right of the interval element. When the interval's timer lapses, we want to read the value of the temperature sensor. Click the interval element to bring up its properties. Let's create a new connector between the interval and the ADT7410 Featherwing element. Click Add Event, and then click ADT7410 Featherwing. We should see a new interval element which reads the temperature in degrees Celsius. To display the value read from our temperature sensor on the application, we need to create a bridge between the embedded workspace and the application workspace. From the element toolbox underneath Bluetooth Low Energy, add a new BLE GAT characteristic. Click the characteristic and name it BLE characteristic temp. Move this characteristic to the right of the ADT7410 Featherwing element. We want the connector to write the value read by the temperature sensor to the BLE characteristic at every single interval. Click the ADT Featherwing element to bring up its properties. Create a new connector by clicking Add Event. Then, click BLE characteristic temp. Now, let's add a Bosch BME 680 environmental sensor to our project. First, we'll need to add the BME 680 to the element toolbox. In the element toolbox, click the Add Element button to bring up the element library. In the element library, search for the BME 680. Click Enable, then click Save. The BME 680 environmental sensor will show up in your element toolbox under Imported. Click the BME 680 environmental sensor to add it to your workspace. Move the BME 680 element underneath the ADT7410 element to give it some room. It's always a good idea to give elements extra space in case we want to add more elements down the road. click the BME 680 sensor to bring up its properties window. Change the I2C address from hex 76 to hex 77 for use with the Feather Huzzah 32. With the BME 680 set up, it's time to connect it to the interval. Click the interval element to bring up its properties. Under its properties, click Add Event. Click the BME 680 element. The BME 680 sensor can read many different types of environmental data, such as relative humidity. Underneath the interval element's triggers, change the BME 680 ability from read temperature to read humidity. Next, we'll want to write the relative humidity read by the BME 680 to a BLE characteristic. From the element toolbox, underneath Bluetooth Low Energy, add a BLE GAT characteristic. Move the characteristic to the right of the BME 680 element. Click the characteristic element and name it BLE characteristic humid. Click the BME 680 element to bring up its properties. Under triggers, change the trigger from temperature read to humidity read. Add a new connector by clicking Add Event. Then, click BLE characteristic humid. The BME 680 can also read the gas resistance. Click the interval element. Create a new connector by clicking Add Event. Click the BME 680 element. Under the BME 680 element's ability, change the ability to read gas resistance. Next, we'll need another BLE characteristic to store the gas resistance read by the BME 680 sensor. Under the element toolbox, create a new BLE characteristic. On the workspace, click and drag the new characteristic underneath the humidity characteristic. Click the characteristic to bring up its properties and rename it BLE characteristic gas. Click the BME 680 environmental sensor element to bring up its properties. Change the element's trigger to gas read. Then create a new connector by clicking the Add Event button. Click the BLE characteristic element. We're done with embedded code for this section. On the top right of the Digi-Key IoT Studio website, click the Save button to save our progress so far. Next, let's click the Application view to open our application workspace. We'll be adding an interval element to read the data from the BLE characteristics we set up in the embedded view. From the element toolbox, underneath Application Logic, click the interval element. On the workspace, click and drag the interval element underneath the toggle switch element. While we're at it, let's reorganize all the BLE elements to the right of the interval element. Once our workspace is organized, click the interval element to bring up its properties. Make a new connector by clicking Add Event. Click BLE characteristic temp. Next, let's add a new connector between the interval and BLE characteristic humid. Click Add Event and then click BLE characteristic humid. Finally, let's add a connector between the interval and BLE characteristic gas. Click the interval element and then click Add Event. Then connect it to BLE characteristic gas. When the interval lapses, the BLE characteristics in the application will read the values sent by the environmental sensors. Let's display the sensor readings on our application by using a new element called Label. In the element toolbox, underneath Application Interface, click the Label element. Move it next to the BLE temperature characteristic. Click the Label element on the workspace to bring up its properties. Name the label Label Temp. Give it some placeholder text like 23 degrees Celsius. And change its text alignment to center. You may be saying, I don't see the label on the application builder. The label is on the application builder, but it's in the background. The application builder supports two layers, a foreground layer and a background layer. Let's bring the label to the foreground layer so we can see it. Click the label element Then, at the top of the application builder, click the Bring to Front button to reveal the label. Click and drag the label underneath the temperature gauge icon. Looks good, right? Let's send data from the BLE characteristic temp to the label. On the workspace, click the BLE characteristic temp element. Click Add Event, and then connect it to label temp. We'll want to display the value read by the sensor along with its respective unit. Click the gear icon on the connector we just created. Read data is the variable value of the sensor as a string. Let's combine it with its unit by setting the text to read value plus quotation degrees C, end quotation. Our application needs two more labels, one to display the gas reading and one for the relative humidity reading. In the element toolbox underneath Application Interface, click the label element. On the workspace, click the label to bring up its properties. Name the label Label Humid. Give it some placeholder text like 15% relative humidity. And change its text alignment to center. Just like we did with the temperature label, bring the humidity label to the front. And move it underneath the percent icon on the application. On the workspace, click BLE characteristic humid event. Create a new connector by clicking Add Event and then connect it to label humid. Click the gear icon on the connector we just created. Let's format this data by sending the text to read data plus %RH. Let's add the final label to the interface. In the element toolbox underneath Application Interface, click the label element again. Move the label to the right of the BLE characteristic gas event. Click the label element on the workspace to bring up its properties. Rename it label gas. Give it some placeholder text like 1200 kilo ohms. And change its text alignment to center. Bring the gas label to the front. And move it underneath the gauge icon on the application. We'll also want to resize this label. You can do this by clicking the dot and dragging it. On the workspace, click the BLE characteristic gas element. Create a new connector by clicking Add Event and then connecting it to label gas. Click the gear icon on the connector. We'll want to show the gas reading in kilo ohms instead of ohms. To do this, we'll need to do some math. Set the text to read data divided by 1,000 plus quotation mark k ohms end quotation mark. The gas sensor is very precise and gives us back a value with lots of decimal places. To keep the app simple, we only want to display the first decimal place. To do this, we'll use the toFixed function in JavaScript and provide it with 1 point of precision. Set the text to read data divided by 1,000 dot toFixed and pass in 1. We've done a lot of work so far. Click the Save button. And then check that your code compiles by clicking the Compile button. Once our code is compiled, let's upload the code to the Feather Huzzah. Click the Embedded tab to switch to the Embedded Workspace. Then click the Program Firmware button. Make sure the correct serial port is selected, then click Program. Open the Digi-Key IoT application on the device. Now, tap the Add Device icon. We should see the IoT Home appear in the Devices in Range list, along with its BLE MAC address. Tap the device to connect to it. On the Configure Wi-Fi settings screen, tap Cancel. The temperature, humidity, and gas values should change on the app. What if it becomes too hot in our home? Wouldn't it be great to have our home regulate the temperature for us? We added a small fan into the home to simulate an HVAC system. When it gets too hot in the house, we'll use the mini relay featherwing to turn on a fan. When the temperature becomes comfortable again, we'll turn the fan off. The ADI featherwing reads the temperature as a floating point value. Unfortunately, at the time of this video, Digi-Key IoT Studio is unable to use floating point values in conjunction with comparison elements. To resolve this, we'll first need to convert the floating point value into an integer value. In the element toolbox underneath Embedded Basic, select the type conversion element. On the workspace, move this element above BLE characteristic temp. Click the ADT7410 featherwing element. Let's make a new connector by clicking Add Event, and then clicking Data Type Convert. Click the Data Type Convert element to open its properties. Change the output type to an integer. Now we're ready to add the comparison element. In the Embedded toolbox, underneath Embedded Basic, click the comparison element. Let's send the output from the convert element to the comparison element. Click the Data Type Convert element. Make a new connector by clicking Add Event, and then click Embedded Comparison. The comparison element compares the input from the temperature sensor to a target value we define. We'll need to define a target value which is too hot inside the house. Set the target value to 25 degrees. Remember, this value is in degrees Celsius. Change the condition to greater than or equal to. Our comparison element will trigger if the target value is greater than or equal to 25 degrees Celsius, or if it's less than 25 degrees Celsius. In the guide, we connected the mini relay featherwing to GPIO pin 33 on the feather huzzah. Let's add a GPIO pin element to control this pin. In the element toolbox, underneath Embedded Basic, click the GPIO pin element. Name it GPIO pin 33. Set the GPIO pin to pin IO 33. The relay will turn on if the comparison element determines the temperature is greater than or equal to 25 degrees Celsius. Click the comparison element to open its properties. Under triggers, make sure the trigger is set when the condition is true. Add a new connector between the comparison element and the GPIO pin 33 element by clicking Add Event. Click the GPIO pin. Click the gear icon to bring up the connector's properties. In the connector properties, change the GPIO pin's ability to set pin high. We'll also want to turn the fan off if the temperature is less than the target value. Click the comparison element. Change the trigger from condition true to condition false. Add a new connector between the embedded comparison element and GPIO pin 33 by clicking Add Event, and then click GPIO pin 33. Change the ability to set pin low. Click the Save button. And then click the Compile button. Once our code is successfully compiled, let's upload it. Click the Program Firmware button. Make sure the correct serial port is selected, then click Program. Open the Digi-Key IoT application on the device. Tap the Add Device icon. You should see your home appear in the Add Device menu. Click the Home. We're only using BLE, so click Cancel. Place your finger over the temperature sensor. Once the temperature increases past the threshold, the fan will turn on. Remove your finger from the sensor. The temperature will decrease and the fan will turn off. Next, we'll use the magnetic door sensor to detect when someone opens or closes the front door. We'll accomplish this by programming the feather huzzah to make a loud beep when someone opens the door. But what if someone enters our home while we're away? Or if we're in another room, we won't be able to hear the alarm. To remotely monitor the home, we'll add an icon displaying the door status to our application. If someone enters the house, we want to be notified about this as quickly as possible. We'll add a second interval element to our embedded workspace. This interval will have a shorter duration so that we can read the door sensor status very quickly. In the embedded toolbox, click the interval element. Click the interval element on the workspace to bring up its properties. Change the interval's name to interval fast, and set the time to 50 milliseconds. We'll move this new interval underneath the interval we already have. Next, we'll need to read the state of the door sensor. In the guide, we connected the door sensor to GPIO pin 15. In the embedded toolbox, click the GPIO pin element. Click the GPIO pin element on the workspace to bring up its properties. Change the name of this element to GPIO pin 15, and set the GPIO pin to pin 15. We will be reading from this pin, so change the GPIO mode to input pull down. Add a new connector between these two elements by clicking the interval fast element. Click Add Event, then click GPIO pin 15. Click the gear icon on the connector to bring up its properties. Change the connector's ability from toggle to read. Let's add another comparison element to evaluate if the door is open or closed. In the embedded toolbox, click the comparison element. On the workspace, let's move the comparison element a little bit to the right. Click the comparison element to open its properties, and in its properties, change the element's name to embedded comparison door. If the door is open, the GPIO pin will read a value of 1. Change the target value to 1. Now, let's add a connector between the GPIO pin and the comparison element. Click the GPIO pin 15 element to open its properties. Under Triggers, change the trigger interrupt to the trigger read. Click Add Event, and then click Embedded Comparison Door. Now that we can detect if the door is open, we'll want to sound an alarm if the door is open. We'll use the buzzer element connected to GPIO pin 12 on the feather to notify our neighbors that someone has entered our home. In the embedded toolbox, click the GPIO element. On the workspace, click the GPIO pin element to bring up its properties. Change the name of this element to GPIO pin 12 and set the pin to IO12. Let's add a connection between the embedded comparison element and the GPIO pin. Click the embedded comparison element. When this comparison element is true, we want to turn on the buzzer. Click Add Event, and then click GPIO pin 12. Under Triggers, Condition True, change the pin's ability from toggle to set pin high. Next, click the embedded comparison door element again. Under Triggers, change the condition to condition false. Click Add Event, and now add a connector to GPIO pin 12. Change the ability to set pin low. Finally, let's add a new BLE characteristic to store the state of the door. In the embedded toolbox, click the BLE characteristic element. Let's reorganize the workspace a little bit. Click the BLE characteristic element and rename the element BLE characteristic door. Since the door sensor is only reading if the door is open or closed, change the read data type to Boolean. Change the write data type to Boolean too. Click the GPIO pin 15 element. Under the pin element's properties, ensure that the pin is triggering on a read. Then, click Add Event. Make a connector by clicking the BLE characteristic door event. Then, click Add Event. Make a new connector by clicking the BLE characteristic door element. Next, we're going to add icons to the mobile application to let us know if the door is open or closed. Click the Application tab to switch to the Application workspace. In the Element toolbox, add a new interval element. We'll be making this interval identical to the one we just created in the embedded view. Click the interval on the workspace to bring up its properties. Rename the interval to interval fast. Change the interval's time to 50 milliseconds. Move the interval element to the left of the BLE characteristic. Now let's add a connector between interval fast and BLE characteristic door by clicking the Add Event button. Click BLE characteristic door. Next, we're going to need a condition element for the application to decide if the value from the BLE characteristic door tells us if the door is open or if the door is closed. In the Element toolbox, underneath Application Logic, select the condition element. Add a connector between BLE characteristic door and the new condition element. We'll be adding two icons to display the door status. One icon is the door when it's closed. The other icon shows the door when it's open. We'll use the technique of hiding one icon and showing the other icon to animate our application. This will look great in the app, but it's a little bit tricky to implement. On the guide, download the door closed image and save it to your desktop. Also, download the door open image and save it to your desktop as well. In the Element toolbox, click the image icon twice to create two image elements. Reorder them so one image element is on top of the other. Click the top image element to open its properties and rename it Image Door Open. Change its image to the door open icon we just downloaded. In the Application Builder workspace, bring the door open image to the front by clicking the Bring to Front icon. Move it to the bottom right of the interface. Click the bottom image element to open its properties. Rename it Image Door Closed. Change its image to the door closed icon we saved earlier. Then, in the Application Builder workspace, bring the door closed image to the front by clicking the Bring to Front icon. Move it to the bottom right of the interface. It will overlap the door open icon, but that's okay. We're only displaying one of these icons at a time. Next up, let's configure the condition element to selectively show or hide triggers based on the door's state. From the workspace, click the condition element. Under Triggers, select Condition True. Create a new connector by clicking Add Event. Then click Image Door Open. Click the condition element again. Click Add Event, and then click Image Door Closed. When the door is open, the condition element returns true. Click the gear on the connector between the condition element and Image Door Open. Then, change the connector's ability to show. We'll want to hide Image Door Closed. Click the connector element connecting the condition element and Image Door Closed, and set it to hide. Next, when the door is closed, the condition element will return false. Click the condition element, change its trigger to condition false, then click Add Event, and click Image Door Open. Add another connector from the condition element to image door closed. Click condition, click add event, and then click image door closed. Click the gear on the connector between the condition element and image door closed. When the condition is false, we want to show that the door is closed, and we don't want to show that the door is open. After the code compiles, click the Embedded tab. Then click the Program Firmware button. Make sure the correct serial port is selected. Then click Program. Open the Digi-Key IoT application on the device. Now, tap the Add Device icon. We should see the IoT Home appear in the Devices in Range list, along with its BLE MAC address. Tap the device to connect to it. On the Configure Wi-Fi settings screen, tap Cancel. Open the door to your home. In our previous videos, we discussed services which can collect, display, and visualize your IoT project's data. While you could use one of the many services we discussed to display the data from your IoT home, Digi-Key's IoT Studio is an all-in-one IoT service. We're going to build a dashboard to help us visualize the sensors inside the IoT home. Just like before, there's no programming. We'll drag and drop widgets to create a dashboard. This will be over a Wi-Fi transport to the Digi-Key IoT cloud, so we can access our home's dashboard from anywhere in the world. The data displayed on our device is not stored anywhere. Every time the interval lapses, old data is overwritten and displayed on our app. This is not very useful if we want to visualize our data over time to detect things like abnormalities. To store this data, we'll need to add a new element to the application workspace called a cloud element. These elements read data from the Bluetooth characteristics we created and send them over your device's Wi-Fi connection to the Digi-Key IoT cloud. In the Element toolbox underneath Cloud, click Cloud Event. Move the cloud above the label temp. Click the BLE characteristic temp to bring up its properties. Let's create a connector between the BLE characteristic and the cloud event. Click Add Event, then click Cloud Event. Let's rename this cloud event element. We're sending temperature, so we should rename it Cloud Event Temp. Let's repeat this process twice to create cloud event elements for humidity and gas characteristics. In the Element toolbox underneath Cloud, click Cloud Event again. Move the cloud event above label humid. Click the BLE characteristic humid to bring up its properties. Scroll down, and let's add a connector by clicking Add Event and connecting it to the cloud event element. Since we're sending humidity, let's change this cloud event name to Cloud Event Humid. Let's save our progress, and then add one more cloud event. This one will be going from BLE characteristic gas to a new cloud event called Cloud Event Gas. In the Element toolbox, click Cloud Event. Move it above label gas. Click BLE characteristic gas. Let's add a connector by clicking Add Event. Click Cloud Event, and rename Cloud Event Gas. Click the Cloud tab to open the Cloud workspace. In the Cloud workspace, we'll notice the workspace is already populated with the cloud events we just added. Cloud events are similar to BLE characteristics, but they bridge the application workspace and the cloud workspace, instead of bridging the application workspace and the embedded workspace. First, let's organize all cloud elements on the workspace. We'll want somewhere to store the sensor data from the home. Luckily, Digi-Key IoT Studio provides 10.49 megabytes of data storage per device for up to 5 devices. We'll use the cloud storage element to store the data sent from Digi-Key IoT Studio to our home. In the Element toolbox, underneath Cloud, click Cloud Storage. While we could send raw data to the storage element, it would be hard to figure out which of the incoming data is the temperature data and which is the gas data. To help identify which value is which, we can associate each value with some extra data called metadata to describe what the data is. Move the cloud storage element to the right-hand side of the cloud events. Then click Cloud Event Temp, click Add Event, and add a connector between Cloud Event Temp and Cloud Workspace. Click the gear connector between Cloud Event Temp and the cloud storage. Under Add Data, change the value to bracket, temperature, value. When we build our dashboard later, we'll notice that the cloud storage element has a temperature entry. Create another connector between the Cloud Event Humid and cloud storage by clicking Cloud Event Humid, click Add Event, and then click Cloud Storage. Click the gear, and then underneath Add Data, change the value to bracket, humid, colon, value, and then end the bracket. Finally, create a connector between Cloud Event Gas and cloud storage by clicking Cloud Event Gas. Click Add Event, then click Cloud Storage. Under Add Data, change the value to gas value. On the top right corner of Digi-Key IoT Studio, click the Save button to save your work. Then click the Compile button. Once the code is compiled, let's head over to the Embedded tab. Click the Program Firmware button. Make sure that the correct serial port is selected, and then click Program. Open the Digi-Key IoT application on your device. Tap the Add Device icon. We should see the IoT Home appear in the Devices in Range list, along with its BLE MAC address. Tap the device to connect to it. On the Configure Wi-Fi settings screen, tap the Cancel button. You should be brought to the application view. We're going to leave this app running and come back to the IoT Studio website. From the IoT Studio sidebar, click the Devices tab. Our IoT Home is already on the Devices tab. Click it. Our dashboard view is empty right now, but don't worry, we'll be populating it with widgets very soon. Digi-Key IoT Studio's dashboard allows you to display your device's data using a variety of widgets. Widgets are visual components that allow you to display device data using different types of visualizations. There's a widget for displaying data as a gauge, a text block, a graph, or even as a pie chart. Let's start by adding a gauge widget to display the temperature from the ADT7410 temperature sensor inside the IoT Home. Click the gear icon on the right side of the page to bring up the Configure Dashboard menu. Then, click the Data Gauge widget. A new data gauge widget will pop up on our dashboard. Click the button with 3 dots to bring up a drop-down menu. Click the Settings button to bring up the widget settings window. In the Configure Data Gauge window, rename the gauge's title to Data Gauge Temperature. Set the unit to degrees Celsius, and change the number of decimal places we would like to display to 2. Next, we will need to select where the data displayed by the widget is coming from. Under Data Source, click Select. Select Cloud Storage, select Temperature, and then click Confirm. Click Save, and the gauge will automatically appear on your dashboard and the needle will move. This reflects the value last read by the temperature sensor. Let's add another element type to display the resistance of the gas sensor. Click the gear icon again to bring up the Configure Dashboard menu. From the Configure Dashboard menu, select the Data Glance widget. A new Data Glance widget will pop up on the dashboard. Click the icon with 3 dots to open the drop-down menu, and then click Settings. change the title to Data Glance Gas, change the unit to ohms, and change the number of decimal places to 1. We can also change the icon of this widget. Change the icon to air quality. If we want to, we could optionally select the time interval this widget updates, ranging from 1 second to 30 seconds. We're not going to do that in this tutorial. Under Data Source, click Select. Select the cloud storage element, and then select Gas. Click Confirm, and then click Save. The Data Glance widget now shows the IoT home's last gas pressure reading, along with the time it was recorded. Let's complete this dashboard by adding a second Data Glance widget to display the relative humidity inside the IoT home. Click the gear icon again to bring up the Configure Dashboard menu. From this menu, select the Data Glance widget. On this new widget, click the drop-down, and then click Settings. Rename Data Glance Relative Humidity. Change the unit to %. And we can also change the icon to humidity. Under Data Source, click Select. Select Cloud Storage. And then select Humid. Click Confirm, and click Save. Let's reorganize these elements a little bit. We've successfully created a dashboard to display data about our IoT home sensors. Now we can view this dashboard on any web browser or mobile device from anywhere in the world.
Thank you, Brent, for the detailed tutorial. As you can see, in just a few minutes, we were able to use Digi-Key IoT Studio to create, deploy, and manage a complete embedded-to-cloud IoT solution. It's simple enough to go from idea to prototype in minutes without any code or tool chains, so you get to explore without heavy investment. Don't forget to check out the hundreds of supported sensors and devices that are fully integrated. Many of the most popular chips in the market are ready for you to drag and drop into your project. And a big thank you to everyone who watched through this series. Whether you are a hardware or software engineer, expert or beginner, you've hopefully learned enough to feel comfortable creating an IoT device that is well-designed, user-friendly, and secure. It's never been a better time to play with IoT. There are so many protocols, boards, and sensors available. What only a few decades ago was literally space-age technology is now only a few cents on Digi-Key.com. Even though this series is over, we're not saying goodbye forever. There's a wealth of resources on Adafruit, from the thousands of tutorials on the learning system to our hundreds of Python and Arduino libraries, all free for you to use. Digi-Key has all the newest tools and parts with links to app notes, CAD files, and engineering resources when you're ready to go to production. And if you're still in that prototyping phase, check out all the Adafruit breakout boards and feathers that Digi-Key stocks. They're a great match for IoT Studio. You could order this evening and get started by tomorrow.